Welcome, everyone. I'm Noah Wilson-Rich. I'm the co-founder and chief scientific officer of the Best Bees company. We manage beehives across the United States for individuals and for companies who want to make an impact. Best Bees is the largest beekeeping service in the whole US. And I'm joined by Darcy Gray. She's also a scientist as well as a beekeeper. As a fellow in the NASA developed program, Darcy applies her skills to identify projects that address environmental and policy concerns throughout the practical application of NASA Earth observations. Hey, Darcy, it's really good to see you.
Hi, Noah. Thanks. Glad to be here.
Yeah. So over this next hour together, we're going to share what we can learn from studying bees, why they're at risk, and what helps them thrive. You'll see amazing NASA Earth observation data that both give us new ways to understand pollinator health and also allow us to shift our perspective on the environment. We'll also empower you with ideas for how to support this research and Best Bees' mission to save the bees. So please feel free to post questions as we go. Shelly is monitoring the Q&A tab, and she'll jump in from time to time. We'll also have an open Q&A at the end of the presentation. Now, many of you joining us today already understand on the surface why bees matter. Simply put, bees equal food. The fate of pollinators is tied directly to the security of our food system and even to human health. These little insects are absolutely essential. Beyond our own nutritional, economic, and emotional well-being, bees of course play a huge role in the reproduction of millions of other plant species. They make the planet as we know it thrive. You might also be aware that bees are in trouble. Last year was the worst to date in the whole United States. 44% of beehives didn't survive the year, and we saw the highest ever recorded summertime deaths. What's happening? The four known reasons are diseases, pesticides, habitat loss, and climate change. Now, most of you logging in here aren't working in agriculture, so you may feel like these macro trends are out of your control. You might think that beekeeping is just a hobby. Maybe it's helpful to pollinate a home garden, but it's not really something that can move the needle on global issues. At the Best Bees company, we're obviously interested in encouraging individuals and companies to get bees. It's fun, it's really fascinating, but we also know that people find value in making a difference. So, just how are we helping people to make an impact? Well, each of our beehives is more than just a box of bugs on a property. They're also living data points that are part of a larger effort to save the bees and to study our world. Now, beyond the direct benefits of food and flowers, and of course honey, bees also give us a view of life and of our planet that we wouldn't otherwise be able to see. This is the focus for today's conversation. By studying bees, we can make a measurable impact to drive real change in accomplishing goals relating to a wide variety of things, including biodiversity, disaster recovery, and climate change. Social dynamics, such as how specialized divisions of labor can help us understand which societies will win and which will lose. These also help us understand the spread of plagues and diseases, things that are very relevant these days. We've got to pay attention. Now, one important takeaway that I want to emphasize is the scientific progress. It's a collective effort that we're working on. No single data point can prove a theory. No single beehive can represent a whole species. And no single person or company can save the bees alone. We're in this together, and it's going to take a grassroots approach to ensure the stability of life on Earth. Luckily, it's happening. Companies around the globe like Fairmont Hotels and the real estate firm Beacon Capital Partners require all of their properties to have scientifically managed beehives that contribute data. And in doing so, they meet investor goals relating to corporate social responsibility and environmental governance targets, while also drawing in new business that favors putting dollars towards companies that value sustainability. These programs add to the company's triple bottom line that we call things that benefit people, planet, and profits. So let's get into some science now, shall we? And towards the end of the presentation, we can revisit how you can take action to help save the bees. Shelly, I'm going to ask you to launch a poll now. So why don't you go ahead and do that?
Okay, now I'm launching a poll. I'd like the listeners and the audience to let us know where you're coming from and your familiarity with a couple of key concepts we're going to cover. This is an anonymous poll, so feel free to be honest and let us know how familiar you are with indicator species, with superorganisms, with the concept of biodiversity, and with honey DNA. Got about 40% voted so far. We'll give it another couple of seconds. Couple more still coming in. All right, I'll end the poll here and I'll share the results so we can see. We've got the familiarity with indicator species is middle of the road, somewhat familiar, kind of spread across the board there. Less familiarity with superorganisms, about 52% are not familiar. 50-50 split, somewhat familiar and very familiar with biodiversity. And most, 55%, or about half, 55% are not familiar with honey DNA. Thank you, everyone. That gives us a good understanding of where we're starting from.
I love this. This feels like we're starting the semester together, and I'm back at teaching again. Thanks, guys. So I'd like to take a minute to cover a quick background on the scientific value of bees. So bees are known as an indicator species. By studying one animal, we can make inferences about others. Bee health likely correlates to the health of the 200,000 less domesticated pollinators, which are critical to our food system and to our overall biodiversity. But they're nearly impossible to observe because they're not social like honeybees. Rather, these other species are typically solitary. They're working hard every day, but going unnoticed, even right above our heads, with estimates of over 300 different species of bees pollinating many parts of the United States every single day. Honeybees in particular are a great species to study since they return to their hives each night and they're extremely docile. Social animals like humans and bees, as well as some other remarkable societies that I love, including ants, termites, naked mole rats, snapping shrimp, as well as aspen trees. All of these share one incredible aspect of strength and unity called the superorganism. Now, only 16% of you are familiar with the concept of a superorganism, so let's have some fun with this. Superorganisms are characterized by specialized divisions of labor, and they're made up of individuals that don't usually survive by themselves for very long. For example, with bees, worker bees are like the blood cells, the queen is like the ovaries, and guard bees at the entrance are like the skin of the beehive, all together considered one entity unto itself, a superorganism. Superorganism theory provides a whole new layer of understanding for the spread of plagues, of conflict and cooperation across groups, and of what factors are associated with the health and success of populations. Studying beehives as superorganisms, rather than individual bees, came in really handy for me during my graduate school days. I didn't have to study millions of bees, but rather hundreds of beehives in order to analyze a large data set at scale. Superorganism theory also helps us scale research across regions, like we've done with NASA Develop, as you'll hear about today. The trends within the scientific community are what's so encouraging to me and my team. There's a lot of enthusiasm for bees in the public domain, as well as sustained activity by researchers at academic institutions, like those that I see in the audience today. For example, to monitor disease, in this case on the slide, what we call a varroa mite infestation, grassroots efforts like mite-a-thons rally recreational and professional beekeepers nationwide to report mite levels in their beehives. As a result, we're able to track the spread of disease and test out promising new treatments. There's great work coming out of Boston University, MIT's Media Lab, and elsewhere, and I'm really optimistic about all the exciting research that's happening. Another trend in favor of the bee's prognosis is a surge of interest in beekeepers among young and diverse talent around the whole world. We feature our next generation beekeepers on our blog, and they're a truly amazing breed. So no, it's not that stereotypical image of a weathered old white man in a field that represents today's beekeepers. We beekeepers are not at risk of dying out. On the contrary, there's a ton of innovation happening in the field. We're defining state-of-the-art beekeeping, where each beehive is a data point, or what we call a living barometer for ecosystem health. With this infusion of energy and new perspectives, lots of ideas, and access to cool technology, we can see where pollinators are dying and where they're thriving. And as a scientific community, we can start to draw conclusions about biodiversity and climate change. I'm going to pause here and ask Shelly to send us some questions. So what questions do you have here? Feel welcome to put them in the chat box.
Sure. One question maybe you can help clarify, Noah, is how long should bees live and how long can a hive live?
So bees live in the summertime about a month for the worker bees. In the winter time, they live maybe 3 to 4 months due to changes in their hormones. In the winter, they're like humans. They don't hibernate. They just eat honey for fuel and cuddle for warmth and a little ball around the queen to keep her warm in the winter. And then hormonal changes will allow them to kind of waken up and start foraging in the active spring, summer season when the flowers are out. A beehive itself, though, should live in perpetuity. It should live forever because the bees can replace a dying queen with a new one. These days, though, bees have been dying off, and so these queens are not being replaced as they should. So instead of a queen living maybe 5 years, it's living under 1 year.
All right, thank you. And how long does the queen live?
A queen could live up to 5 years or so. It's really fascinating, actually. It's not well understood how a queen is chosen because it's just a female egg. So out of thousands of female eggs laid every day by queen honeybees, it's not well understood why one particular egg is fed a different diet called royal jelly, the fountain of youth substance, that allows her to live for years instead of what all the other female eggs are living about a month.
Great. And last question for this break here. How can I/we ensure better success of survival of the hive so far north, for example, in New England?
Yeah, it's amazing to think that Canada and Russia have amazing beekeeping and pollination operations. They do a lot of farming much further north than New England, and a lot of farming requires pollinators. So when we think about honeybees and winter, it can be really challenging, but the key here is to breed locally adapted pollinators or to promote the native species that just go unnoticed. So the more we can understand what plants that are native to any given region, for example, your question was New England, we can think about promoting more of those plants to encourage good nutrition, as we'll get into a little bit today, so that those pollinators are very well locally adapted to whatever conditions they might be. In this case, winter, in other cases in the tropics, maybe more rainy seasons.
Great, thank you. Great questions rolling in. We'll keep moving and revisit these questions towards the end. Thank you.
All right, thank you. All right, now we've caught your attention by promising NASA grade science. So let's go there. I'll turn it over to Darcy, who has a great way of explaining how we used satellite data for advancing a mission like ours. And I'm so glad that she's joined us today for this conversation. So Darcy, please feel free to share your slides whenever you're ready.
Thanks, Noah. And yeah, thank you everyone for joining us today. I'm pulling up my slides now and hopefully you can see them all right. Yeah, so as Noah mentioned, I'm Darcy Gray and I'm the fellow with the NASA Develop program at Goddard Space Flight Center in Greenbelt, Maryland. And a couple summers ago, Best Bees partnered with NASA Develop in the summer of 2018 on a project that used NASA data to look at some of the variables and some of these complex questions around bee health. So today I'm going to talk to you about this project that the team of Jeremy Rapp, Victor Lenski, Eob Solomon, and Ryan Young completed. So you might be asking, what does NASA have to do with honeybees? Something that often surprises people is that a large part of the research done at NASA is earth science research. And NASA has a network of satellites which look down at Earth and collect data. And this is what we mean when we refer to NASA Earth observations. So these satellites collect images with cameras that give us a way to visually view Earth from space. But many of them, through different methods, also capture metrics that we can't see with our eyes. So things like thermal radiation, precipitation, infrared, and some other non-visible light sources. NASA Develop is within NASA's Applied Science program, and Develop coordinates or collaborates with decision makers to conduct short-term feasibility projects that apply NASA Earth observations, so those data from those satellites you just saw, to address environmental issues. And these projects engage young professionals, typically recent graduates, early career professionals, or current students, and decision makers in 10-week-long projects that identify opportunities to use NASA data, NASA satellite data, to create methodologies and tools for project partners. So this directly supports the individuals working on the projects, as well as the institutions who are the partner organizations, and ultimately increases the use of NASA Earth observation data and enhances decision-making and policy making as well. So every year at Goddard Space Flight Center at our develop location here, we complete several projects, and in 2018, one of those was the New England Food Security and Agriculture Project. So these are some of the factors that are associated with bee health, but we also know that there are relationships between these that can have compounding effects. And we can't look at all of these things from space, but we are able to look at some of them on scales that would otherwise be impossible. So, there's so much complexity to the honeybee environment relationship, to any pollinator environment relationship. And while scientists have a number of tools to investigate this, like Noah was saying, no tool is really going to provide a full picture on its own. So what this project really aimed to do was just provide end users with a way to visualize some of the factors that we know are associated with bee health from space, so that the partners could make decisions about hive placement and could also start to explore some of these variables and maybe the relationships that we might not be seeing yet. So the project partnered with the Bee Informed Partnership based out of University of Maryland, Bee Counted, and the Best Bees Company's nonprofit arm, the Urban Beekeeping Lab and Sanctuary. So if you lived in an apartment in this building in Boston, and you had the opportunity to set up a rooftop beehive, it would be pretty easy to make the assumption that this is not a hospitable environment for honeybees, because that's just what you see from the ground. But looking from above, even just with this Google Earth image, which doesn't necessarily allow for you to do complex analysis, you can already start to see that there's actually plenty of not just green space, but trees. And there's even a water body. And bees have a foraging range that's estimated anywhere up to 5 miles, sometimes even more than that. And it's not easy to understand what that range looks like when you're standing on the ground, even if you do know that there's a park around the corner. So looking from above really allows you to characterize the space a little bit better. So basically, this project wanted to do that in a way, but also look at some of those variables that I mentioned earlier that we don't just see in one picture. So that includes things like time series and some things that satellites can capture, even though we can't see them with our own eyes. So the objectives of the project were to create a tool that allowed the partners to explore potential apiary locations. And then this tool would be able to ingest ground data and ultimately help the partners make decisions about where to place hives. And the team also put together a tutorial for the partners on how to use the tool. And as you can see from this picture, the project team was even lucky enough to join the Bee Informed Partnership in the field for a day of data collection. So the team sought to incorporate data into the tool that would help, as I mentioned, these honeybee researchers untie the complex knot of bee health factors. So there were a number of variables that went into this from different NASA satellites. So the team used the cropland data layer, which is developed by the US Department of Agriculture, and it's based on the Landsat IX satellite. And this data layer not only classifies land cover type, but it also distinguishes between crop types, which is really important for honeybees because, as we know, bees sometimes show more of an affinity towards some crops like almonds over other ones like blueberries. Elevation data from the shuttle radar topography mission was used. And since elevation is connected to temperature and humidity, users will be able to examine its relationship to honeybee health. And this allows us to look at macro scale elevation changes. So we're looking less here at the changes between a 2 and 20-story building and more about the changes in the physical geology. Precipitation data were gathered from the Global Precipitation Mission. And we know that humidity of a hive is really important and that bees work pretty hard to moderate the humidity and keep it between 50 and 60% humidity to encourage better egg hatch rates and lower pest rates. So we knew that precipitation would be something or the team knew that that would be something good to look at. And soil moisture, using the soil moisture active passive satellite was integrated because soil moisture supports vegetation, which then subsequently supports honeybee diets. So it was one way to sort of look at that forage availability question. And then the main way that the team really looked at that was using two different vegetation indices, which are EVI and NDVI. So that's Enhanced Vegetation Index and Normalized Difference Vegetation Index. And those are from Landsat, sorry. Sorry about that. Those are from the Landsat satellite, and then EVI is from Sentinel. Something in my throat, but I'm powering through. Okay, so yeah, these vegetation indices give the team the opportunity, or the end users the opportunity to look at greenness, and they're really capturing different things here. So EVI looks a little bit more at canopy structure, and NDVI is about chlorophyll. It's a proxy for chlorophyll, so photosynthetic activity of the plant. Basically, the team put all of these variables into a tool that was constructed in Google Earth Engine, and that's an open source platform that allows you to explore satellite data, conduct analyses, and build tools like this one. So when a user opens the tool, you can either, they're able to either hover over an area and click on it. So say they hover over Princeton, and they're going to get a point for their potential apiary. And this is represented by this black circle, the radius of which depends on what the user put for the foraging range. And so they can either hover and click on the map, or they can upload points to the map as well. Then the map populates with all those variables that I just mentioned. So this here is a composite of satellite imagery that's helpful for visualization, and upon which many of these other variables were, or a couple of the other variables, especially the vegetation indices, were built. So you can actually go through and look at each month of the satellite imagery, which can be really informative for beekeepers. But the indices that the team used were based off of composites, and using a composite allows you to take the best or most cloud-free pixels from a whole summer or a year, and then get really the most characteristic image of a site and build a vegetation index off of that. So this is that cropland data layer, and this distinguishes between land cover types and specifically between crop types. And it also provides a histograph that's in the corner there, which tells you which of the land cover types is the most prevalent, which then your selected foraging range. And this is nice because it allows the viewers to quickly kind of identify what the dominant vegetation type is, and what the diversity of vegetation that is available to each hive is. The elevation layer gives researchers the mean, the max, and the min elevation, as well as allowing them to visualize it. And when looking at hives across multiple locations, elevation in correlation with some other variables may give rise to trends not previously known. So I think the team was thinking that this would be a good thing for the partners to be able to explore. So for example, hives in the Rocky Mountains seem to be not as productive as hives in similar climate conditions in low coastal beaches. So there might be some factor that elevation is playing there. Our NDVI and EVI, so those vegetation indices, these layers will allow researchers to investigate links between vegetation productivity, available water content in the leaves, and those potential links to honeybee vitality and forage availability. Also, time series data will be displayed for quick reference within the tool, and this can also be exported for use in statistical analysis. The time series of these vegetation indices, which represent greenness throughout the year, are especially relevant under changing climate conditions, as they'll allow the partners to sort of look at how the seasons could be changing or how there could be an anomaly in one year, which you can imagine is really critical for honeybees, since earlier springs could mean earlier blooms, and we don't fully know just yet what that means for honeybee populations. Our tool allows users to generate exploratory analysis like that you've seen in the app itself, as well as to export any of this Earth observations data or the graphs that they calculate for use in other statistical tools or in GIS or other geospatial analysis tools. So as I mentioned, this research was carried out over the course of 10 weeks. And just like any research, it had certain limitations. So one of these that's a common limitation when looking at a single species from space is that we're looking at the habitat on a landscape scale using pixels that are 30 meters or larger. And so that means while we are able to generally characterize the habitat surrounding a hive, the diversity within that pixel isn't going to be fully represented. And honeybees are small insects and they're able to access microhabitats, and we can't fully capture that from this kind of data. We can just get more of a characterization of the general surrounding habitat. Additionally, there's so much complexity in any ecosystems, but pollinator-plant relationships are particularly complex. And so there's a lot of factors that play a role in this that aren't captured from space. Including management by beekeepers and pesticide exposure, other things like that. Another limitation is that those vegetation indices we talk about look at the greenness or canopy structure of each pixel, which in itself doesn't hold significance for honeybees, but is here used as a proxy for availability of plants that bees could forage at. However, as we know, not all plants have equal quality for honeybees, so that's, again, not fully represented here. And Noah's going to talk a little bit later about one potential solution to that when he talks about honey DNA. And when using ground data collected from beekeepers, of course, it's important to remember who these people are submitting the data, and access to submitting data with Bee Counted and Bee Informed is easier for people with reliable internet connections. Additionally, the tool itself, the one that you just saw, it's designed for the partners to use, and while it is open source, so anyone can access it on the NASA developed GitHub, it does require a baseline understanding of coding, so it's not entirely equitable and accessible to everyone who might want to use it. But ultimately, what I think this project gave us and what the team did a really great job of doing is giving some great insight into what can be accomplished with satellite data looking at honeybee habitat. And there are a lot of great possibilities that this draws attention to. Of course, it'd be great to expand the exploratory zone of this tool. Right now, it just is available for Connecticut, Massachusetts, Rhode Island, and New Hampshire. And it's pretty scalable wherever similar available data is. And additionally, being able to add forecasting and suitability capabilities to this tool would be a really great way to give qualitative ranks to each site. And looking at native pollinators in this way could also provide insight for habitat provision and protection. So a lot of these factors are really applicable to native pollinators as well, but having a tool that is more specifically geared to land cover types that might be more attractive to native pollinators could be really cool. So as I mentioned, the tool was created in 2018, and a lot of really great stuff has happened since then. So I did want to draw attention to one example, which I've shown here, which is the Beescape tool. And this is an open source tool made by a team at the Center for Pollinator Research at Penn State in partnership with a couple of other universities. And this site, which I would encourage you all to check out, actually lets you compare between different locations. So here I've clicked 3 sites on the left, and it sort of ranks them on the right. And it ranks them on things like nesting sites, so that's really applicable for native pollinators, insecticide exposure, and spring, summer, and fall floral abundance. They're also starting to use some satellite data to explore this. As you can see on the bottom left, they have that same cropland data layer in there, so you can start to look at that. But I think overall just kind of gives you another good idea of how geospatial information can be used to look at honeybees. And yeah, lastly, our other future work could include looking at that honey DNA data or other, specific floral information in conjunction with satellite data to really paint a full picture of forage availability for honeybees. And so before I hand it off to Noah about that, I do want to just thank all of you for joining us and for...
Oh, I'm going to fix her audio there. Darcy.
Hi.
Hi. Your audio is kind of going crazy. So I reset you. Can we give you an audio test real quick? I know you're wrapping up on your side here.
Oh, no worries. Can you hear me all right now?
Yeah, it's a little rough. There are some questions though. Let me see if I can give you a chance to. I know you're on a hotspot, so I'm not sure if that might be related. So the one of the questions from the audience is when you click on a map and a circle appears, how many miles/kilometers is the radius of the circle? A technical question for that tool. Audio sounds good now too. Thanks.
Okay. Cool. Hopefully I'm audible now. Yeah, so great question. Sorry, I forgot to mention that. So the foraging range is adjustable. The picture you were looking at, that was 3,000 meters. But when you open up the tool, you can input any foraging range that you want in meters. Yeah, and thank you.
Great. And I think, Noah, do you want to answer
Sure.
the follow-on question that I would have to that answer is how far can a bee fly?
Yeah, it's such a good question. There are some amazing researchers out there who have looked into this. Heather Matilla comes to mind. She's at Wellesley College in Massachusetts, and I like to call her the bee whisperer. I haven't really called her that to her face yet, but I'm sure she wouldn't be insulted. She can watch a bee's waggle dance. So this was Nobel Prize winning research by Carl von Frisch in the 70s to understand this dance communication language of bees. And so Heather Matilla can watch this dance language, watch a bee dance, and then she knows where to go to the flower patch. And she said that bees can fly over like 70 kilometers. She's Canadian, so she'll use kilometers instead of miles. But it's a really long, far way. And I think that there's a lot of exciting research to better understand just the languages of superorganisms, to understand even with humans how we can be our best societies too. So we commonly say 3 to 5 miles. Sometimes bees might not have to go as far. Sometimes if resources are limited, they'll probably have to go quite a bit farther.
Great, thank you. Darcy, another follow-up question for you. How do NASA develop projects get selected?
Yeah, great question. Thank you. So we select projects in a number of ways. The fellows, so the folks in my position, sometimes reach out to partners and suggest those ideas, which I believe is what happened in the case of this project. I was not the fellow at the time that this project happened. The partners also sometimes approach NASA Develop. Sometimes people just think up a good idea. And if you have an idea of a project, you can visit the NASA Develop website and fill out the project idea submission form there.
Great, that might be a good answer for this next question. Have you considered combining the develop work with machine learning to predict potential favorable habitats?
Yeah, that's a really great question. And there's some really cool work happening there, I think at Oberlin. But, you know, one way I see that being used is training, potentially using some, maybe that honey DNA data or ground data to train a model to identify specific species based on their spectral signatures from the satellite. Could be really cool to show us then where, you know, because we know where crops are, but for native species in forests that support native pollinators and for trees in cities and that kind of thing, being able to train a model to identify those could give us a better idea of where the best suitable areas are, and also what can be done to supplement suitability for bees and native pollinators in other areas.
Great, thank you. Noah, I'll hand it back to you.
All right, great. Let me reshare my screen here. Okay. Well, Darcy, thank you so much. That was awesome. So now I want to share a little bit about what we do with these data. How do we apply them? So we apply the NASA developed algorithm that Darcy just showed, so that back-end science behind it, to help us to better understand where bees are experiencing the most health on the ground. For example, how do we know what plant habitat was like for them? How do we know how this relates to their health? It's one thing to better visualize where bees are thriving, but it's a whole nother next step for us to truly understand why they're thriving there. So for our next step, we use this concept that we call blue zones. Maybe some of you have heard of these from studies of where human longevity is quite long. So where octogenarians, or people living over 80 years, are common, such as Japan and the Mediterranean. We looked at our data and we wondered, what can we learn about blue zones for humans that apply to bees? Do these geographic areas hold the key to our own future health? And are there explanations that are similar for why we see advanced health in both humans and in bees in places like these? So to bring it back down to Earth, from going up into space, I want to ease us all back into what we take home from this. So here's where we stand. Our current hypothesis is that nutrition plays a key role in beehive productivity and longevity, just like what we understand about human blue zones. Now, bee nutrition is thought to correlate with biodiversity. This was another one of our poll questions, and most of you, 95% actually, are very or somewhat familiar with biodiversity. In short, this term refers to the variety of living species on Earth. So this includes plants, animals, bacteria, fungi. It's a healthy ecosystem that has a rich level of biodiversity that we're really looking to thrive towards. My lab needed a way to measure bee nutrition to further investigate this hypothesis. But how does one measure the nutrition of superorganisms at scale and without much of a budget? How do you read the nutrition label of a flower patch, or of a home garden, or a country farm, or a building rooftop, like what we saw in Darcy's slides? Well, it turns out that we actually had gallons of evidence right under our noses. We decided to do a deep dive into the biology of honey. We sequenced the genome of pollen found in honey that we harvested from our own beehives. We called it honey DNA, and Best Bees is the only company to offer this analysis. Honey DNA was our fourth poll question, and 55% of you are not familiar with it. So let's get started. We'll have some fun here. Honey DNA now informs us about the plant environment surrounding beehives. It measures ecosystems like never before by using advanced genomics to look at DNA, just like Ancestry DNA or 23andMe do for humans. Maybe some of you have done those. For example, my home beehive, the honey DNA report from my own honey said that the third floor deck beehive there that I use as a cocktail table, located in Boston, has 411 total plant species in a single spoonful of honey. So every time I tasted my honey, there were maybe 411 different flavors. The genetic makeup actually changed over the course of the year, with 25% coming from apples in the spring, and then due to shifting plant blooms, changed to 32% linden trees in the summer, followed by 13% from pine as the dominant nectar source in the fall. Now, by zooming in to what we call a bee's eye view and mapping the DNA genomes using this cutting-edge technology, we're now measuring what plant types are out there for pollinators, also what proportion exists for each plant, as well as the timing of their blooms year over year across small micro levels of habitat for each 3 to 5 mile radius that the bees fly from each beehive. In addition to measuring a habitat's nutritional value for bees, there's practical applications for honey DNA that we realized circumstantially. Honey DNA is a snapshot of a local ecology that's suspended in honeycomb. It can serve as a record for communities who need to rebuild, telling them what vegetation and what proportions were originally present in the area. As climate change causes more destructive natural disasters, we're more frequently faced with rebuilding a local environment after devastating fires, droughts, floods, hurricanes, and tsunamis. One of our next projects is to overlay honey DNA data with satellite data so that beekeepers can start to understand what we can do to transform habitats to improve pollinator health, perhaps by promoting a wider variety of native plants in each area where bees are just not doing well. The survival of bees really does come down to each and every one of us. So here's how you can do your part. Advocate for bees. Use your voice, your Instagram, your Facebook pages to share information about bees. Look around the physical spaces and resources that you have and consider what more can be done with them. A vacant corner of a rooftop can actually have a really big impact. So ask your employer, what are you doing with that empty space? Let's turn it into a small garden or pollinator habitat. Plant native wildflowers. Even though it's almost autumn and we don't usually think about planting flowers at this time of year, there's still great things that you can do. Planting now yields flowers in the spring. You don't have to wait. For more on what to plant, we'll post a few resources to the chat now. If you don't think of yourself as a gardener, try guerrilla gardening. Take a handful of native wildflowers and throw them in a vacant lot and see what grows. We can all help improve the greenness of our local ecology no matter where we are, no matter your age or your ability. Get bees. Professionally managed beehives are a low maintenance and high impact option for those interested in expanding bee populations. Each beehive managed by my team, at least, adds to the larger data set for ongoing research. Even the beehives that die still count as data, and therefore they're still valuable to science. The fact that a hive doesn't survive, it still tells us something. Or you can take a local beekeeping class and do it yourself. I also suggest joining the Bee Informed Partnership, but please don't neglect your beehives. Commit to it, or you can make it worse by spreading mites and disease. Get honey DNA reports. This is sort of like getting your dog's DNA report, but the data will actually inform disaster preparedness efforts. It'll identify the presence of invasive species and even serve as tasting notes for your next charcuterie platter with your friends, which you can even do virtually these days. Honey DNA lets you learn about your bees and what they like in your own area. If you don't have beehives, you can get this analysis for a friend. And lastly, use the NASA data. For both the professional scientists and the citizen scientists in the audience, tap into RSET. That's NASA's Applied Remote Sensing Training Resource. It's a mouthful, I know, but it's awesome. It covers the basics, for those of you who have never touched it before, to more advanced topics, and it includes live and on-demand free webinars. This RSET resource is for anyone who wants to learn more about how to use satellite data to investigate questions for almost anything. So, speaking of questions, let's take some more of yours. Shelley, let us know where you'd like to start.
Sure, we've got a couple follow-up questions. One is, how do you see this data playing a role in the conversation around climate change?
Yeah, I think it's so exciting to have some data to support and advance our conversations about climate change. So here's what's really fascinating about what Darcy showed and what we showed. These are snapshots in time. So when we're thinking about change, that always has a time element. So let's say we're talking about climate or any other kind of change, society change, whatever. When we have measures and images and participation for what things look like over time, we can now advance what we're talking about. So climate change isn't a dirty term. It's something that we're just visualizing. And as a collective society of humans, we're just better understanding what this means, how this impacts our lives, and also what the history is going back and how we can make some prospective decisions going forward. For example, seeing how a population might impact the ecology, what we can plant, what things were lost after a hurricane, what grasses are the most resilient against storms or fires and can help prevent coastal erosion. So by understanding what was lost, we can better plan ahead for what we want the future to look like.
Great, thank you. Another one for you, Noah. Have you found anything artificial or strange in the honey samples that you've done DNA analysis on?
Yes, we found a lot of weird things. So we found, I was going to give a big talk at the University of Wisconsin for Earth Day this year. And one of the things I love to do with Outspoken Agency is I give these talks where I get a sample of honey in advance. And at the talk, I'll debut the results and say, hey, Wisconsin, this is what your honey DNA profile looks like. This is what you're tasting in honey. This is what you can consider planting more of to promote bee health in your area. Now, I mentioned with honey DNA and my results from my home in Boston were 411 different plant species. To date, that is the highest number of species we found in a sample of honey. The lowest to date was 52 from just south of Boston. in a town called Duxbury. Now for Wisconsin, if you want to think in your heads right now what number that was for plant diversity from the range of 52 to 411, think where you think how diverse the plants are and how good is the habitat in Wisconsin. It was 2. And I looked at those and I said, this is insane. This talk is going to be really impactful to show everybody you need to plant some more things here. But I started to think and dig deeper and I realized, wait a minute, I think this is artificial honey. So I went back to the source and I said, where did you get that? And actually it wasn't from a local source. They said, oh, we just got some cheap honey bear stuff from the dollar store. And so it actually, we understood that it was artificial honey. It wasn't the real stuff. Some other interesting results, even for my own house, we did see a little marijuana from the environment. And we've also found some endangered species of plants.
Great, thank you.
Yeah.
So follow-up question for you, Darcy, from Ray. And I'm not familiar personally with this acronym. Was MODIS, M-O-D-I-S, considered for land classifications?
Hi, yeah, great.
It's like a technical question I can throw at you.
Yeah, good question. So I'm pretty sure the only land classification that the team used was the cropland data layer. I don't think they classified, like built their own land classification or trained a model because, you know, they only had 10 weeks. A lot of times other developed projects do use MODIS or Landsat to you know, do a random forest classifier and then use that in the model, but MODIS was not used for this project.
Okay, another question, Noah. I'm not sure, you guys might want to tag team on the answer of this one. This is from Jeff. Are there any data sets suggesting the ideal ratio of forageable cover types relative to hive density or typical forage radius to rate and delect plants?
I'm not familiar with that just yet. I think it's kind of an exciting next direction for this research to really keep considering the applied value of all of the algorithms and genomics that we're working on. How do we keep translating this into something that can be really impactful for those of you who are stewards of land? So I'm going to take that question as a suggestion and we'll keep working on that and get back to you, Jeff.
All right, so another question, I have always heard it was a bit of a misnomer that at farmers markets and other such places where people sell honey that people can claim to sell wildflower honey or lavender honey. I guess the Honey DNA project could put those arguments to rest.
Yeah, one of the things I love about this technology is that it can really add value. So when we talk about this new world triple bottom line, people, planets, and profits, these things all work together in an additive way. So people have heard of Manuka honey that comes out of New Zealand and it's trademarked by the government. So even though it does come from the Manuka plant's nectar, even when the Manuka plant is somewhere else in the world, like from Great Britain, it can't be called Manuka honey because like champagne, it's grown from a particular region. And so the consumer pays a higher price for that honey. So Best Bees has done some work with the World Bank and countries like Haiti, or even partnered up with the government of Ethiopia to help people understand what their honey is. When we say wildflower honey, and you can get that from a lot of places, but by adding value through science, I'd like to say, once you know what your product is, you get a little test and then you tell people, here's what my honey is. From India, we know it's oak honey. That's really cool, a taste of India. This is what India tastes like. From the Bahamas, it's avocado and cinnamon honey. So it's really fun to know what you're tasting. It's crazy that even in this modern world, we still don't know what our food is. We just call honey honey. It's been thousands of years, 15,000 years of humans eating honey. So there's a lot more work to do to better understand our food, what it is, to help our food system, and also for beekeepers and honey producers to make some more profits, God forbid, through science.
Great, another question for Darcy. This one's from Christy. I am an engineer at the company that built the OLI instrument for Landsat 8 and for Landsat 9, due to launch next year, September 2021. What could make this instrument and the data it generates better for your research? A little product research question here for you.
That's a very exciting question. Thank you. Yeah, I think like advanced resolution of Landsat 9 will be really exciting to look at. Right, I think the chance to characterize more specifically what the foraging range or what the forage availability is beyond just saying, you know, this has high NDVI and this has low NDVI, so we can extrapolate that that means this is good forage and this is, you know, less suitable, would be really cool. And I think has implications beyond just like New England. Obviously Landsat's a global satellite, and the idea that there could be this like higher resolution, you know, higher spatial and temporal resolution data that could look at, that could be used to characterize forage would be really cool. And yeah, I guess I don't know all that much about the OLI instrument, but I think like the links as well to temperature that could be provided from Landsat 9 could be really cool, because there's also some suggestion that swarming and absconding, for example, in African bees, could be caused by you know, physiological limits being exceeded in terms of temperature, which would have major implications for climate change. So that would be really cool as well.
Great question. Question from Byron. Can DNA tests show exposure to pesticides? Is there a way to measure the health of bees in relation to if the plants around them were treated with pesticides over the season?
It's such a great question. The answer is no, unfortunately. So pesticides don't have DNA, they're chemicals versus biology. So what we're looking at is you know, signs of life, things that are living. So unfortunately, we can't use honey DNA or genomics to look at pesticides. Pesticide testing is often available through government services. It can be limited. It can also be quite expensive. So our ability to understand the relationship between pesticides and our bees and our greater environment, it's a bit limited at the moment. But we've done a little bit of work with the Harvard School of Public Health to do some surveys around where pesticides are affecting beehives. Beehives are really good sentinels for, as we call them, bioindicators for environmental health. So if we're trying to find out the pesticides in the environment, we can use beehives. And even though it's not a genomics test of the honey, we can do other pesticide tests to look at the accumulation in the environment of these pesticides that are out there. So slightly different test, kind of limited right now to government agencies, a little bit expensive, but it's still in the honey that's where the answer lies. And since honey never goes bad, it really is suspended in time. So we could even think about a climate change approach to looking at pesticide exposure in the environment, because we can just keep these samples of honey around over time until that type of research test does become more widely available and more affordable.
And that also relates to the lead tests that happened after the Notre Dame fire, correct?
That's right. How amazing. So with the Notre Dame fire, there were beehives there. Paris is thought of to be the birthplace of urban beekeeping. And so there's a lot of questions about environmental air quality. Now, when the big fire happened at Notre Dame, the beehives did survive that fire, and they served as a way to measure the amount of pollution that was in the air. A lot of people were suspecting that there was pollution coming from the fire, specifically lead and other heavy metals. Well, there was a way to look in the honey and in the beeswax of those beehives to actually measure this. And yes, there was lead that was released into the air. Luckily, the research showed that that was at a level that was safe. You could still consume honey that has a little bit of lead in it and other heavy metals. But now we know how much lead is in the environment. So again, through bees, we now understand the toxins that are in our environment and at what levels.
All right, so fascinating. So last question, good one from Ron. How can I get my honey tested for DNA?
Yeah, so check out bestbees.com. So that's a great resource. We'd love to answer your questions. So reach out to us anytime. The Better Bee catalog also has it too. So just reach out anytime, send in samples from around the world. It's something that we're also working on with our nonprofit website. So that's urbanbeelab.org. We'll have a website upgrade soon that will have a map. So talking about Google Earth Engine here, a picture just hovering over on the map to any place around the world. Let's say India, you know, just a favorite around northern India, we see a lot of oak. You can hover over those dots where we had samples from and then see the honey DNA report. So it's a great way to share in a free open access way to the world about what our environment looks like, complemented very much with Earth observations and these beautiful satellite images. So a citizen science grassroots approach to better understanding the world we live in.
All right, now that's the end of the questions. I'll let you wrap it up.
Okay, all right. Let's see if I can get this again. Okay, well, Darcy, thank you again so much. To our audience, I want to thank you guys for your attention. The Best Bees Company's mission is to improve bee health and to expand the bee population. By taking a scientific approach to beekeeping, we're striding towards that goal. In the process, we're securing our food system, we're pollinating our gardens, we're harvesting delicious local honey, and we're supporting research into many important facets of life on Earth. Please let us know what you thought about this presentation and stay safe out there. Thank you.